So we're off to, I think, nomenclature, as we did finish up, I think, bonding last time, chapter 4. A reminder, in terms of chapter 4, you're responsible for obviously whatever we covered, which was mainly should be geometry and it should be hybridization. There is a molecular orbital theory, I think, as well in chapter 4. We are not going to cover that. So, you're not responsible for anything that involves a molecular orbital theory from chapter 4, because nobody wants to do that, I don't think. All right. So what we're going to do, actually, I think, is go backwards, back to chapter 3, where I think nomenclature is talked about. So we're going to go back to chapter 3 and cover pretty much all nomenclature here and make sure everybody's on the same page in terms of how to properly name things, write formulas, and so forth. So obviously, nomenclature is about really naming compounds. And really, nomenclature, for the most part, is broken up into the two types of bonding that we talked about. We name things that are ionic compounds, which, as we talked about with bonding, are metals and non-metals together. And as we talked about with bonding, we do get the electron being transferred, or electrons being transferred. And the result of that transfer of electrons is we do end up with ions, which are obviously things that are charged. So we do end up with cations. And we do end up with anions, which obviously are negatively charged. And as we talked about with bonding, once again, there is no sharing of electrons here. It is actually just the electrostatic attraction between the positive and negative guys that basically hold that together. So the way that we sort of name ionic compounds is different than the way that we name sort of covalent compounds or molecular compounds, which, as we talked about with bonding, obviously are two nonmetals together. And here we have some type of sharing of electrons. And as we talked about, again, that sharing may be equal or maybe unequal. Not really important in terms of the naming part of it. But again, these type of compounds are named differently than ionic compounds. And we'll also get into, towards the end as well, talking about naming acids and how we go about sort of naming those guys as well. So obviously that is the periodic table, which is a good thing to know. But one thing to know, obviously, from the periodic table is, as we might have talked about, like somebody just posted, noted the periodic table over there. All right, so there's a lot more blue dots on top there than there used to be. When we talk about the periodic table and we talk about elements off the periodic table, remember that things really do not have charges until they really start kind of hooking up with each other. And more specifically, they really don't get charges unless they kind of form an ionic compound, a metal and a non-metal coming together. But when that does happen, there are certain things that do have fixed charges, and that's pretty much everybody in group 1 is +1. Everybody here in group 2 is +2. Group 3 is +3. It's, for the most part, aluminum is really the one that you kind of deal with the most. So it kind of goes +1, +2, +3. Then we kind of skip group 4 there. And then going from group 5 to 6 to 7, we're talking really about our nonmetals. So kind of up and to the right of the staircase here. That's -3 here in group 5, -2 in group 7, and -1 in group 7 -1. Group 2, group 6 -2, and group 5 -3. So these guys have fixed positive and negative charges. For the most part, our transition metals here have a variable charge, the variable positive charge. In addition, even outside sort of the transition metal region, sort of in this region where we do have things like lead and tin, which are metals sort of underneath the staircase, they also have a variable positive charge as well. Now, there are sort of 3 exceptions in terms of transition metals that, although they are transition metals, they actually do have a fixed charge. And again, that is sort of like this little backwards L starting at zinc. So zinc and cadmium, both of those guys there. Zinc and cadmium will both always make a +2 charge, no matter what the situation is. And if you hang a left over there at cadmium, you head over to silver. Silver also has a fixed charge of +1. So those three are sort of exceptions for our transition metals. They also have fixed charges, but everybody else sort of in that transition metal region does have the ability to sort of make a multiple sort of charge situation depending on what they are sort of attached to. Any questions on that there? So when we talk about ions, there are the two types of ions. There are cations, which are positively charged, and these guys are usually coming from metals. So if we have just a cation by itself, we do want to write the formula that includes the charge. So if you did have, any of these guys, for example, we would include the charge in the formula. And how we go about naming cations is pretty simple. We just frankly use the whole name of the element. So we just use the whole name of the element. So this would be the hydrogen ion. We do put ion at the end because it is a thing with a charge. This would be the lithium ion. This would be the calcium ion, and so forth. So not too bad. The sort of metals that have charges or cations, just simply whatever the whole name of the metal is, and then you just put your ion at the end of it. Now, anions are a little bit different in terms of how we go about naming guys that are negatively charged. Anions, which are negative charge, and they usually are nonmetals, they actually do get the last part of their name kind of dropped, and we replace it with IDE. So we kind of replace the last part of the name with IDE. And if we were to write again, just some guys here with negative charges like H minus, Br minus, O2 minus. This is hydrogen, so this actually becomes the hydride ion, ION. This is bromine. We drop the last part of bromine, it becomes the bromide ion. Oxygen, we drop the last part of oxygen, and this becomes the oxide, or a little bit more maybe than the last part of it, ion. Now, as you can see there, hydrogen is an unusual element. It is really one of the only ones that could kind of go both ways. It can be positive, and it is positive usually in most cases. It can be negative though, and it can be negative when it follows after a metal. So if you had something like LiH, this would be lithium hydride. And this would be made up of a lithium ion and a hydride ion here. Any questions on ions and how to name those guys? So here is, again, a sort of a table of those guys, and you can see our negative guys gets the IDE treatment. Our positive guys is really just the name of it. Now, when we do take an ionic compound and we do take a cation together with an anion, we always want to put these guys together so that the formula always equals 0 in terms of the charge. So for example, again, if we took something like calcium that has a +2 charge, and we took bromide, which has a -1 charge, when we put these guys together, we actually need more of the Br to balance it out. We need 2 of them. That gives us a -2 overall to balance out the +2. And that gives us the proper formula here of CaBr2. So whenever we do write a formula for an ionic compound, the actual formula for the ionic compound that contains the cation and anion should never have an overall charge. It should balance out to zero. The reason it needs to balance out to zero is, again, what we talked about with bonding. What really is happening here, and the reason why we need to do that is, again, calcium has its 2 valence electrons. Br has 7. So when calcium goes to lose its electron, it needs, as we talked about, an extra Br there to allow it to reach noble gas configuration. So this is really the reason why, as I mentioned, probably when we were drawing that, that the reason why we do balance out the positive and negative charges is it allows everybody to reach that noble gas configuration in terms of electrons, which, as we talked about with bonding, is really the goal of bonding, is to reach that noble gas configuration. So it's important to remember that when you do write the formula, it should have no charge, but it should also be remembered that it actually is made up of several things in this particular case that does have charges. So it's really made up of, these 3 guys that do have charges, but overall for the formula, we represent it with no charges. So if you were asked to write the formula for the cation here, this is what you should write. And if you were asked to write the formula for the anion, you should write one of these guys, is what you should write, not like 2 of them. You shouldn't write this or anything like that. You should just write the Br minus, would be the correct way to represent the anion in this particular case. Any questions on that there? Okay. So the first type of naming we're going to talk about is sometimes referred to as a type 1 compound. And a type 1 compound always has a metal and a non-metal, which automatically, you should know from our bonding conversation, that is an ionic compound. Because we have a metal and non-metal, we are going to get that transfer of electrons, creating our ions. And pretty much in naming, whenever you have a metal involved, that is really the most important thing. The non-metal is not that important. It is always the metal that's kind of important in terms of how you go about naming things. So as soon as you see the metal and non-metal, it is always the metal that is the most important. And what makes this a type 1 compound is actually the location, if you will, of the actual metal. So a metal here that is from group 1, group 2, group 3, or if it's zinc, cadmium, or silver, makes this guy basically a type 1 compound. And what all these guys have in common is what we just talked about a second ago. They all have fixed positive charges. So again, it's always the metal that's most important. And again, if you have any of those guys, it will tell you have a fixed positive charge, which frankly means that's all you need to worry about at that point. And you proceed to naming it. And when we name a type 1 compound, it is a pretty simple formula. You pretty much use the whole name of the metal. And for the non-metal, you drop the last part of the name and you replace it with the IDE. So very simply, whole name of the first of the metal, IDE on the second. That's all she wrote. So if we take something like NaCl, we look at this. This is a metal. Cl is a non-metal. Once again, it is the metal that is the most important here. And that is group 1, which means that's all we need. We use the whole name of the metal, which is sodium. Chlorine gets the IDE at the end of it, and it becomes sodium chloride. If we take the one that we did a second ago, CaBr2, the name of this guy would then be, this would be calcium bromide. Once again, this is a metal. That is a non-metal. The metal here is group number 2, which means it is a type 1 compound. So we go with calcium, and bromine gets the bromide IDE treatment. Now, this is a situation where this 2 right here has no effect on the name. We do not use prefixes or anything like that because we think it sounds more scientific or anything like that. So you do not use a prefix, has no effect on the name. You could have 40 of them there. You would still just call it bromide at this point. That says 1, 2, 3, group 1, 2, 3, zinc, cadmium, or silver. Other questions? So we don't use prefixes here. It doesn't matter how many of the non-metals you have. It doesn't matter actually how many of the metals you have either. You just simply use the whole name for the metal and the IDE for the non-metal. The reason obviously the 2 is there for what we talked about in the previous slide, because our calcium has a +2 charge, we need not 1 of these bromides, but 2 of them to balance it out. But again, has no bearing on the actual name. Any questions on type 1 here? All right. So why don't you try some here? And since I already did that one, we'll swap this guy out for something else. Let's do this. And then why don't you write the formula for these guys here? Let's go with calcium nitride. Let's do aluminum oxide. And let's do a little potassium. And let's do potassium phosphide. All right, names on the left. All right, let's take a look, see how we're doing. So first one here is KCl. That is a metal, that is a non-metal. So once again, it is the metal that is most supported. We find potassium there in group 1, which means it has always a +1 charge. So it is a type 1 compound. So we can proceed to the whole name of the metal here, which would be potassium. And our chlorine here would get the IDE treatment. The cation here is K+. The anion is Cl- in this particular case. What's that? You don't. No, you just need to give the name of this one. But if you were asked to write again the formula for the cation or anion, those would be what you would write. Yeah. Other questions? Next one is ZnS, which is zinc. Zinc is a metal. Sulfur is a non-metal. Once again, the zinc here is a transition metal, but is one of the 3 that actually does have a fixed charge. So again, it does fall under type 1, which means once again, we will go with zinc and put the IDE at the end of it there, zinc sulfide. The cation here would be zinc with a +2 charge. The anion would be sulfur there with a -2 charge. Again, why we just have 1 of each of them in the formula there to balance it out. Rolling through there, we got Li2S, so that's lithium, which is a metal. And again, our sulfide there, which is a non-metal. Lithium is group 1. Which means it is going to be a type 1. So this would be lithium. And once again, our sulfur will get the IDE treatment. The cation here is Li+, not Li2+. It is actually Li+. The 2 means there's 2 of them there. Yes, there's 2 of these guys, each with a +1 charge. So there is no thing as Li2+. Well, there might be, but not in our case. There's not. The S here, the anion is again, the S2- would be the formula there. Lastly, here we have barium, which is a metal. We have hydrogen, which is actually, again, a non-metal. This is a case where hydrogen is actually coming after the metal, which means it's actually the negative version here of hydrogen. And that's why there's two of them to balance out the positive barium there. But in this case, it's still the barium that's the most important, and barium is group 2, which means it does have a fixed charge. So that's going to be barium hydride. Any question on any of those names there? All right, so going to formulas from name, we basically want to just take the parts and put them together to equal 0. So calcium here is group 2, which means it should be a +2. Nitride IDE is nitrogen from the periodic table, which is group 5, which means it has a -3. So when we put these together, we basically need to get to 6 for each of them. So that's going to give you 3 calciums needed and 2 nitrogens needed. Again, giving you -6, and your 3 calciums giving you +6 happening there. Any question on that one there? Aluminum is group 3, which means it has a +3 charge. Oxygen there is group 6, which has a -2 charge. So once again, putting this together, we're going to get to the 6 number just by multiplying the 2 numbers together. Gives us 2 of the aluminums needed and 3 of the oxygens. Lastly, here we have potassium, which is group 1, and we have phosphide, which is group 3. As a -3 in this case, we need a few potassiums there to balance it out. That gives us K3P in this case, and we would have the right formula. Any questions on that there? Now, sometimes people teach you again just to kind of do that move, and it works most of the time, but not all of the time. So you'll get some wrong. So if you blindly just do that, you'll come across a number that it really won't work, but it does work a lot of times. But you really shouldn't just blindly do it, because there will be a number of them that won't work correctly. Yeah. Any questions on type 1 compounds here? All right. Then let's talk about type 2 compounds. Type 2 compounds are also ionic, also a metal and a non-metal. And once again, it is the metal that is the most important, and our metal is going to be a transition metal, or just to the right under the staircase. So those would be, again, those elements like lead. There's antimony over there in the sun, I think, some tin in that area. Those guys also, although they're technically not transition metals, they could have multiple positive charges. So they're really named kind of the same way here. So because these guys could have a variable charge, we do have to sort of do one additional step. We pretty much name it the same way as a type 1. We're still going to take the whole name of the metal. We're still going to do the non-metal there that ends in IDE. The additional thing we're going to add to this one is a Roman numeral. And the importance of the Roman numeral is it is the positive charge on the metal. So if you took one metal out, what the positive charge is, it is not how many you have, which is a very common mistake that people make. It is actually just that positive charge is on it. The reason we need to do that is to tell people, in this case, this is the guy with the +2 charge, or this is the guy with the +3 charge, because they could have multiple types of charges. So for example, if we had FeCl2, in this case, we would look at this. Iron is a metal. Cl is a non-metal. Once again, it is the metal that's most important. We would find the iron in the transition metal region, dead center, and that should tell you that it could have multiple charges. So you're like, I'm not maybe sure. The good news is you will always know the charge or whatever it's attached to. So that is Cl, which is group 7, which means it has a -1 charge. And there are 2 of them, which means overall we got a -2. So to balance it out, the iron here has to have a +2 charge. And then that's all we really need for our name. We would go with iron, Roman numeral 2. And again, the 2 is for the charge. And once again, even though there are 2 of the Cls, it has no effect on the name. No prefixes here. This would be chloride. So this would be iron Roman numeral 2 chloride. Once again, the reason we need to do that is because if we took something like this guy here, this guy here would now be iron Roman numeral 3 chloride. And that is because our iron there, not sure, but in this case we have not 2, but we have 3 of the chlorides, meaning that our iron in this particular case needs to be 3 to balance it out. So we need to tell people that that is the one that we are dealing with. Any questions on that there? All right. So here's some of our guys. You could have obviously multiple charges. We still have our fixed guys there. Remember, these guys again are type 1. And even outside the transition metal region, those guys also are named this way. Now there is an old name and a new name, which you could clearly see on this slide right here. We will only use Roman numerals in this class, but you still sometimes see people use some of the older way of naming. So for example, ferric or ferrate, that is iron 3 or iron 2. Cupric or cuprate. And again, that would be copper 2 and copper 1. I think I got that. What? Try that backwards. There we go. 3. Other way around. Cupric would be 1, and that would be 2. There we go. It's so old I haven't done it in a while. There you go. But we use the ending there, ic or 8, and actually we don't. We use us, huh? I'm using something older than that there. This is what I learned. Yes, I'm that old. I didn't learn it that way. Thank you very much. It's ferrous or cuprous. There you go. So we won't use these older names, but they do pop up occasionally. We'll use just the Roman numeral part of it. All right. So why don't we do some here? Let's give some names of these guys. PbO2, we'll add to the list there. Let's do nickel 4 chloride. All right, so let's take a look. We got CO, which is cobalt. That is a transition metal, along with Cl, which is chlorine, which is a non-metal. So once again, this is going to be ionic. We're going to look at the cobalt, which is the most important. It's in the transition metal region. So once again here, we would need to sort of maybe figure out what the charge is. Looking at our non-metal, though, we do know that it is group 7, which means it has a -1 charge, and there are 3 of them, which means this is going to be a +3 charge. That means we'll use the whole name here of cobalt, Roman numeral 3, again for the charge. And once again, doesn't matter how many we have, it will be chloride at the end. Any questions on that one there? Looking at the next one, which is copper, also a transition metal. Iodine, they're a non-metal. So once again, looking at the copper, we got to figure out the charge. We could do that easily by seeing that I there is group 7, so it has a -1 charge. That means that the copper, to balance it out, will be a +1 charge. That means that this would be copper, Roman numeral 1, and iodide here at the end. Again, the charge there. In this case here, we got SN, which is tin, which is not a transition metal, but it is named the same way because it could have variable charges. We have our Br, which is group 7, which has a -1 charge. And you could draw them all out if you like. That's going to give us a -4. That means this would be a +4. And this would be 10 Roman numeral 4. And once again, it would just be bromide there at the end. Any question on any of those there? Last one here, this is lead, which is a metal, oxygen, which is a non-metal. Once again, lead just to the right there, but named the same way. So if we figure out what the charge is, we know oxygen is group 6, has a -2 charge, which means that's -4, which means this is +4 in this case. This is lead Roman numeral 4 oxide, not 2, where you do your switcheroo and get the wrong number. Yes. So this is an example where you cross over. If you're not paying attention, you might call it lead 2 and be incorrect in this case. So any questions on any of those names there? All right, so to write the formula here, we're going to kind of work based on what we're given. So when I see nickel Roman numeral 4, that means my nickel has a +4 charge. I don't need to figure that out. It basically tells me. The chloride is group 7, which has a -1 charge. So in this case, we need more of the chloride to balance it out. And need 4 total chlorides there to give us a -4 charge to balance out the +4 charge. Copper Roman numeral 2. Once again, that tells me the charge there on the copper. Our oxygen there is group 6, which has a -2. In this case, just need one of each of those to balance out the charge, giving us CuO in this case. By the way, not C2O2. Yes. And lastly, here we end up with 10 Roman numeral 2. So 10 is SN, and it will be +2 in this case. Nitrite is nitrogen, which is group 5. So that's a -3. So once again, here we're looking for basically 6 there to get us balanced. So to get the 10 to 6, we need 3 of them. And to get the nitrogen to 6, we need 2 of them in this case. So. Any questions on any of those formulas? Yeah. So type 1, no Roman numerals because the metals have a fixed positive charge, so you don't need to tell people which one you're dealing with. Type 2, you do need the Roman numeral because they have variable charges, so you need to tell people, hey, I'm dealing with the +2 or the +1. But neither have prefixes anywhere. So if you find yourself writing a prefix and a Roman numeral, you should just also write yourself a big X over it because it is incorrect. Yeah, so there's no mixing of any of those things together, even though everybody always wants to do that. All right, so sort of a decision tree here. And again, always when a metal is involved, that is the most important thing. So you want to always look at the metal to determine whether or not really in these two cases here, if you need a Roman numeral or not. So let's talk a little bit about polyatomic ions next. Polyatomic ions are actually groups of nonmetals that are actually bonded together through covalent bonding, but end up with an overall charge. So for example, if we had NH4NO3, this right here is actually 2 polyatomic ions together. We could break it up right there in the center of the 2. There. And coming this way, this would be NH4 plus, and coming this way, this would be NO3 minus. This 1 nitrogen and 4 hydrogens, they're all covalently bonded together. They stay together, and the overall thing has a +1 charge. We probably drew this Lewis structure, I think, maybe, but it looks something like this. We are covalently bonded, sharing electrons, but still has a charge, so it's still an ion in this case. This one nitrogen and 3 oxygens also all stay together and has a -1 charge overall. We also drew this guy, I'm pretty sure, which is nitrate. And this whole thing has a -1 charge. So ultimately, even though they're kind of groups of nonmetals together, they still are basically a cation and anion, which means there's still a positive negative thing put together, which means we still want to balance it out to 0. So that is why in this case, we basically have +1 coming together with -1. We just need one of each of those guys. Each of these polyatomic ions have individual names. This guy here is what is referred to as the ammonium ion. Not to be confused with ammonia, that does not have a charge. This is the nitrate ion. The good news about polyatomic ions is you just use the name. So in this particular case, since we have 2 polyatomic ions together, this guy that I originally wrote there would be ammonium nitrate. Now, I will say that probably in most cases, most polyatomic ions are actually negatively charged. Ammonium is one of the few sort of positively charged polyatomic ions that you come across. So what happens, I would say probably in 9 times out of 10 cases is you're going to have a polyatomic ion that's pretty much going to be hooked up with a metal. And the metal is going to act as the cation and the positively charged. So a lot of times when we deal with polyatomic ions, because they pretty much hook up with metals, we really do just fall back to what we just talked about. Once again, when a metal's involved and a polyatomic ion. This guy's going to be the negative guy. This guy's going to be the positive. Once again, it is the metal that's most important, and you would follow either the type 1 rule or the type 2 rule, which means either you got to lay up a Roman numeral on the metal or you don't. And it's the same reasoning as we use for type 1 and type 2 ionic compounds. And that is probably, like I said, 9 times out of 10, how you'll deal with a polyatomic ion. It will be attached there to a metal. So here's a list of some polyatomic ions. Yeah, I think so. So a vast majority of polyatomic ions end in one of 2 ways. They end in either ate or ite. And you could kind of group a lot of ions together by how they are related to each other. So if we look at something like NO3 minus and NO2 minus, again, they both have a -1 charge. The difference between them is the number of oxygens they have. The one with the most oxygens will end in ate, so that is nitrate. The one with the least number of oxygens will end in ite, so that would be nitrite. Same thing, it doesn't really matter about the charge. You could have something like SO4 2 minus and SO3 2 minus. Once again, each of these have a -2 charge. The one with the most oxygens here would be sulfate and sulfite. So that's a really good way to learn them, kind of group them together by what's related. There are also groups of 4 that are related to each other. The most common group of 4 is ClO4 minus, ClO3 minus, ClO2 minus. Can you turn it off? Yeah. ClO minus. Every single one of these guys has a -1 charge here. So really the only difference between them all is the number of oxygens. And we could break this up kind of the same way. Everybody to the right here has the least number of oxygens, so they both should end in ITE. So this would be chlorite. And this guy would also be like chlorite, except obviously you can't have the same name for 2 different things. So in a group of 4, the one with the least number of oxygens will end in ITE, but also start with hypo. So that is what is known as hypochlorite, chlorite. Going to the left, these are the guys with the most oxygens. So they both would be chlorate, ATE. And same idea there. You can't have obviously two names that are the same. So the group of four where there is the most oxygens will also start with per in front of it. So that is perchlorate, chlorate, chloride, and hypochlorite. Cl is a halogen. You pretty much could swap out for any halogen in that group of four, and it's named the same way. You could do something like BrO3 minus. So instead of chlorate, this would be bromate. So it kind of works the same way. Put an I in there, it's iodate and so forth. So you could swap out any of those guys for any of the ones here, and you could do that. Now, a lot of times what people can do or will do is you can remember all the eights and know that the ites are basically just one oxygen less, or you could do the opposite. Remember all the ites and know that the eights are just one more oxygen above that, or you can just remember them separately, however you like to do that. A couple other things that we see on this table, if we go back to it maybe. If we take something like CO3 2 minus, that is carbonate. And if we put not just an H, but an H plus onto it, like a proton, we will end up with HCO3 minus, because it's not just a hydrogen, but it is +1 and -2, gives us -1 left over. We basically put a hydrogen on it. So this would be hydrogen carbonate. And hydrogen carbonate is also sometimes called bicarbonate instead of hydrogen. Just like sulfate's the same thing. You could put an H plus in front of sulfate and it's hydrogen sulfate or bisulfate. Those are two commonly still used sort of terms for those guys. Other things that we see is not all polyatomic ions actually do end in ate or ite. Something like OH minus is hydroxide, CN minus is cyanide. So there are a few polyatomic ions that actually do end in kind of IDE at the end of it. So you do have to know these, yes. Formulas would be helpful as well, so you can balance out everything and the names that go with it. Any questions on that there? Now, we talked about never sort of using a Roman numeral and a prefix together. This would be the only place where it would be acceptable, and it would be acceptable because the actual polyatomic ion has a prefix in its name. So we got like dichromate. It has the di in its name, so that's okay. But other than that, there should never be your own prefix added with a Roman numeral. But some of these polyatomic ions like dihydrogen phosphate has a prefix in it, so that's obviously okay if you did that. So let's try some here. Let's go with Na2SO4. Let's do CuNO3 Let's do FeSO4 E2. Let's do ammonium sulfide. Let's do potassium hydroxide. And let's do chromium. All right, let's take a look. So we'll start here. So we got a sodium, which is a metal, and we have a polyatomic ion, which is sulfate. Once again, once the metal gets involved, it really determines how you go about naming it. So the sodium is a type 1 numeral because it has a fixed charge. So we actually just roll right into the name, which would be sodium. And once again, we use the whole name for the polyatomic ion, and that would be sulfate, bless you. And that would be sodium sulfate. The anion here is sulfate with a -2 charge. The cation is sodium with a +1 charge. And once again here, that's why we need 2 of the sodiums to balance out the charge to 0. Any questions on that one there? Coming to the next one, we again see a metal, which means that's important. We see another polyatomic ion there. So our metal here is a transition metal, which tells us it's a type 2 compound, which our metal, which means it can have variable charges. So we do want to figure it out. We know that nitrate is NO3 minus, and once again, there are 2 of them. That gives us a -2, which means in this case, the copper is a +2 charge. That means we do need a Roman numeral. So this is going to be copper Roman numeral 2, once again for the charge. And once again, it doesn't matter how many of those polyatomic ions, we're just going to use the name of it. So this would be copper Roman numeral 2 nitrate. Any questions on that name? And looking at the last one here, we have iron, which is a transition metal. We have sulfate, once again, which is a polyatomic ion. So here we actually have not 1, but we do have 2 of the irons. And we got 3 of the sulfates, each at basically -2. That gives us a -6, which means in this case, each of the iron is a +3 to balance it out. So our name here would be iron Roman numeral 3, not 2 or 6, but 3 for the charge on one of the metals. And once again, here we will just do sulfate at the end. Any question on that name? Now, why is there parentheses around these polyatomic ions? Yeah, because there is more than one. So whenever you have more than one polyatomic ion, when you do write the formula, you do need to put parentheses around it. Otherwise, if you did not, obviously you would end up with something like this, which would mean you have 43 oxygens, which is really not what you're intending. So we always got to make sure there is more than one polyatomic ion, that we do parentheses it up and put the number on the bottom. Coming on the other side there, we want to write some formulas. So basically just going to get the units here. So ammonium is NH4 plus. And sulfide is actually just sulfur off the periodic table, which is group 6, which has a -2 charge. So here we're basically putting +1 and -2 together. So we actually need more of the ammonium here. And once again, this is a polyatomic ion, so we will need to put parentheses around it, and a 2 at the bottom and an S. So NH4 2S would be our correct formula. Tells us we have 2 of the NH4s, each at +1, gives us a +2 to balance out the -2 that we have for the sulfur. Any questions on that one there? Potassium is K plus, group 1. Hydroxide is OH minus. So we are good to go on that. That is going to be a KOH situation. Chromium Roman numeral 3 means that my chromium has a +3 charge. Carbonate is CO3 2 minus. So once again here, common number there is going to be 6. So to get my chromium to 6, I need 2 of them. To get my carbonate to 6, I need 3 of them. And once again, we would need some parentheses there to look something like that. Yeah. Any questions on polyatomic ions? Again, probably that is the most way that you will use them is with metals, basically. Any questions on that? Okay, so our journey through naming continues here. We're going to then talk about acids. So acids are basically substances that can produce H+ ions in solution. When we talk about acids, H+ H3O plus, which is the hydronium ion, also a polyatomic ion, is basically the same thing. This is also sometimes called a proton, and that's because hydrogen has a proton and an electron and no neutrons. So in order for it to become positively charged, it loses an electron, which leaves it just a proton. So that's why it's sometimes called a proton in acid-base chemistry. So acids are, as I mentioned, something that has the ability basically to produce H plus ions in solution, which means acids are aqueous solutions. It's kind of the same thing. And they should always be given the AQ symbol, which basically means it's a water environment. The difference between AQ and L is a pure substance like water. And if you take water, you take some salt and mix it together, you get a sodium chloride solution that gets the aqueous symbol. So it's usually something kind of dissolved in something like water or something like that. So acids will always have the aqueous symbol, and that is how you can distinguish, for example, the difference between if you have just HCl, that's a gas, and HCl, that is an acid. This, by the way, when we have hydrogen that comes in front with another nonmetal, it is really treated like a type 1 compound, even though hydrogen is a nonmetal. It's really H plus and Cl minus. So this would be hydrogen chloride. So although hydrogen, again, is really a nonmetal in terms of names, because it sort of acts as an acid in a lot of cases, we kind of just use it like a type 1. So if you have HCl in the gas stage, that would be hydrogen chloride. In the aqueous or solution stage of it, it becomes what is known as hydrochloric acid. So the aqueous is actually important to distinguish that you are dealing with an acid versus, say, the gas version of it. And obviously, you would name it slightly different as well. So when we do name acids, it all revolves around oxygen. So it's all about basically oxygen. And if the answer is there is no oxygen, the way we go about naming our acid is it will start with hydro something ic acid. Now, for all acids, they're basically thought of as ionic and compounds. The cation is always H plus. So H plus is always the cation. The anion obviously is the negative part, and that is what would go into here, the anion that it is attached to. So if we look at something like I just wrote there on the previous slide, HCl, there is no oxygen. This would then be hydrochloric acid. HBr would then be hydrobromic acid. So if your acid does not have oxygen in it, it should always start with hydro, it should always end with ic, and the middle part there is going to be your negative guy. Again, in this case, the cation would be H plus, the anion would be Br minus, hence the bromide part of it is where the name comes from. Any questions on acid? No oxygen. So if your acid does have oxygen, it is sometimes considered a oxyacid because it has oxygen, hence the name oxyacid there. So oxyacids are acids that obviously have oxygen. And if it does have oxygen, it will also contain everybody's favorite thing, which is a polyatomic ion. So if the answer is yes to the oxygen, it will contain a polyatomic ion. And as we just talked about, pretty much they end in either ate or ite. And the way that the polyatomic ion ends determines how you name the acid. So if your polyatomic ion ends in 8, your acid is something-ic acid. Once again, here the cation is going to be the H plus. So if we take something like HNO3, this has obviously oxygen. It has a polyatomic ion, which is nitrate, ATE. This then would be nitric acid. We do H2SO4. That has oxygen. It's an acid. SO4 is sulfate. This will be sulfuric acid. Once again, here our cation is the H plus. Our anion is the sulfate, which is why in this particular case, we needed 2 of the H pluses once again to balance it out to 0. So you can think of acids really as like ionic compounds for the most part, and you want to balance out their formula to 0 using H plus as your cation. Question on either of those there. Now, if it does contain oxygen and your polyatomic ion ends in ITE, then your acid name will be something OUS acid. So if you had HNO2, NO2 does contain oxygen, that is nitrite. So this would be nitrous acid. If you had H2SO3, that is sulfite. That would be sulfurous acid. Same thing here. Our cation would be the H plus, and our anion in this case would be the SO3 2 minus. There is absolutely no what in this name. There is no hydro. Yeah. So hydro is only for acids that have no oxygen in it. So if it has oxygen, you should not be using hydro. And obviously, if it does not have oxygen, that is when you should use hydro. Any questions on that? You can remember it. You ate too much, you feel icky or not. Something to think about. That's how they taught it when I was way back in my day in school, way back with the stone, all that kind of stuff. All right, so let's try some here. Let's do H2S. Let's do HClO4. Let's do carbonic acid. Let's do phosphorus acid. All right, let's do names on the left there and formulas on the right. Take a look. So we'll start with the first one here. I do not see any oxygen. So we're going to then go into our hydrosulfuric acid. Again, the sulfuric part coming from there. Any questions on that one there? Coming to our next one, we do see oxygen. So that means we do have a polyatomic ion. That is ClO4 minus, which is perchlorate. Since that ends in 8, that means that my acid should end in ic. And that means that this would be perchloric acid. Any questions on that one there? Now, if we want to write the formula, we could just work our way backwards. And if you're not sure, you could dissect the name. So that's carbonic. So it ends in ic, which means there is no hydro. So it is a polyatomic ion, right? So we could get rid of the ic and put 8. So that is carbonate, which means that is what I should write. And my cation is always H plus in this case. And that means I need 2 of those H pluses. So that would be H2CO3 to balance it out. Gets me my carbonic acid. Yeah. Any questions on that there? Same approach here. We got phosphorus acid. So once again, I don't see a hydro, so I know it's an oxygen containing guy, which means it should be polyatomic ion time. That is OOUS, which means basically it's ite. So that's like phosphorite. So that's like phosphorus fluorite, which is PO3 minus. And once again, our H plus here. So we need 3 of those guys to balance it out. H3PO3. We should write the aqueous symbol next to it when we're writing formulas for acids to indicate that they are acids. Any questions on how